I've got talking and flew away from us.
You're already on slide 8. You've done well. Is Google recording? Before I start, yes, it's on. Good, thank you. Just making sure we have our other people watching along as well. So the session that we're now going to do is talking about pinched and gated injection. And it's not a huge topic, but it is a very important one because it needs you to get your head around where things move in an electric field. So we've got a full hour for it. I don't think we're going to use the whole time that we've got dedicated. But I hope that I'll get you all through and be able to draw how to do an injection on a chip, because that's my aim for this afternoon session. We had Professor Philip talking about injection in CE and the fact that we can do that hydrodynamically or electrokinetically. Hydrodynamically, just using the siphoning effect, where we either apply some pressure to one of the vials containing the background electrolyte to then force a little bit of liquid into the capillary, or we literally just hold up one vial a little bit higher than the other and then let it down again after a little bit. That creates the hydrostatic pressure as well, and we get a small amount of our sample injected into our capillary. Unfortunately, with the chip, it's hard to break it and then lift one of the reservoirs up, but there's separate ways of doing injection as well. Before we go to the traditional ways, I first want to say that the siphoning approach, it does work in CE chips as well. Here we've got some work very early on that I did in my thesis when we had a micro channel that actually didn't have an intersection, no interface at all for the separation. I don't have a mouse there, then we'll go with the laser pointer. So you can see the device layout here. It was a serpentine to have some length, but it only had an inlet and an outlet. And what we did is have some two different reservoirs on there. One where we could put the sample in, one where we always had the buffer sitting in. We had a pipetting robot that could empty both vials. So the liquid was primed, was cleaned, and the channel was filled with our background electrolytes. We then got the robot to first only fill the sample reservoir with some sample, which means that the liquid level here on, is a lot higher than it is here, which means that we get a tiny amount of sample hydrostatically being pushed into the microchannel. Then we filled the other reservoir with buffer, removed the buffer from here, had a little bit of a wash to make sure there was no carryover of our sample, and then we filled our buffer reservoir with buffer as well before we could apply the separation difference. So again, we had background electrolytes, 1 or 2 squiggles of sample, hopefully still less than 10% that we need to have a good resolution in CE. And then we had the rest of our channel filled with background electrolyte, this reservoir as well. It worked. We didn't get great peak shape, so we probably injected about 20, even the minimum time that we could have the sample in there. We probably injected about 20% of the channel length, but it can be done. Another version of hydrodynamic injection in CE that I've already shown you was when we were talking about the hydrodynamic resistances. Mind you, here we've got the system where we've got 2 electrophoresis channels, and we've got an intersection here with a wide channel where we have the sample coming in, and we also have 2 buffer streams that are shielding that sample stream away from the inlets of the separation channels, so we wouldn't have any cross-contamination. Because of the significant difference in flow resistance between this microchannel combined with this bit of tubing here and the wide channel here with the valve open, 99.99% of the liquid went straight ahead when this valve was open. However, when we stop the buffer to have only sample here and we close the valve, the pressure develops, and that hydrodynamically injects a little bit of sample into our 2 separation channels. We can then open the valve again, flush through buffer so that we've got our channel here filled with background electrolytes. All the sample is removed, and we've got our small plug of sample, less than 10% of the separation length, in both separation channels, at which point we can put on the potential differences. Here you can see the electrodes, the center electrode here, the center of the chip was grounded. So we had ground, negative and positive potentials being applied, and we could do cation and anion separation in both directions because we had hydrodynamically injected a small sample plug. And we looked at a picture there where you can just see after the injection the tiny amount of red dye that's injected at either side, using that sequence of events and playing around with hydrodynamic resistances. We purely did that to do things differently and to look at if we could do some capillary electrophoresis for monitoring. We've heard yesterday that for the forensics, sometimes you need to revisit what you're doing in order to get something that's got a commercial edge. And the reason that we developed this injection system is that we want to continuously take a sample from a river and then analyze it by capillary electrophoresis to do environmental monitoring. A lot of other sample injection methods are not that compatible with being used 500 times without manual intervention. When you do it this way, you need big bottles of buffer, you need your pumps, but you can do it. You can do 500, 600, 700 repeat injections autonomously without any need of human interference. However, the rest of the world since the early 90s has been doing cross injection, and we'll later on see the improved version of their doing pinched injection. So what's happening here, we've got a device very similar to one of the ones that I passed around yesterday. It's called a cross-channel device. We've got a long channel to do our separation. We've got 2 channels to put our analyte in and have somewhere a waste bucket to have things to go as well. And we've got a third reservoir where the background electrolyte can be in. What we do during injection is that we move our analyte from the sample reservoir towards the reservoir that we call sample waste. You can see here, it may be bleeding a little bit at the intersection, but you can see that we get a red line from the bottom to the top. The way that we achieve that is that we don't use a pump, we use a potential difference. So if we've got a negatively charged analyte, we make this reservoir positively charged, this one negatively charged. Electromigration will take your analytes in a straight line. If these 2 reservoirs are not at any potential, if they're left floating, the analytes have no curiosity, they don't want to go there, they want to go in the direction of the field lines. Electrophoresis is very easy. If there's a straight line, the analyte will take a straight line. So the analyte does take a straight line. What you can then do is switch your power supplies and then stop the potential difference in that direction. We'll apply, we have a negative analyte, so your negative electrode here, positive electrode here. What then happens is that all analytes that are sitting at that intersection, they all of a sudden realize that they're in electric field again. So they go with the electric fields that is this time in the plane, in the horizontal plane of your screen. This allows you to inject a very nice, discrete and small injection plug in a microchannel. We're now going to see, in Australia, we've got a comic which is called Where's Wally, which is looking at the differences. What's different in this picture here? This is what we had before. This is where we're now. What's different? Little hint is given here. This is called the pinched injection. And it looks like someone is kind of pinching the flows here. Again, this is all done electrokinetically. And what you do here is that in addition to the negative and the positive, so having negative electrode, positive potential, but your analyte's going, you now also engage the electrodes you anyway have sitting in your reservoirs to later on do your separation, to also apply a small potential, which then means that the bleeding that we had on the previous slides is not a problem anymore because everything gets pushed into a very small zone because the anions from the buffer and the buffer waste channel also move towards our sample waste. So we've got our analyte, our sample, moving from sample to sample waste towards the positive electrode because there are anions. We've got the anions from the buffer reservoir and from the waste reservoir doing the same thing. And we get a very nicely defined small injection zone. And we've said before that a small injection zone is important in capillary electrophoresis because it allows us to get higher resolution and it allows us to get the resolution we want to have using a shorter channel, which means a smaller microchip, which means cheaper. Everybody likes cheap. So that's the way that we call pinched injection. To look at that a little bit more schematically, but mainly because there's a movie in here, they've got the system rotated here. So we again have sample, sample waste, buffer, and buffer waste. Here we've got the different scenarios that we spoke through. So initially, if we've got our negatively charged analyte, got our negative polarity here, positive polarity here, analyte wants to go straight over the cross-section. We also apply a small negative potential to our buffer and our buffer waste reservoir. So we get pinching, we get that flow cut off to prevent any bleeding and bulging out here to the sides. We then change the potential difference towards having here in plane where we go into the separation channel to allow our sample zone to be surrounded by background electrolyte, and we can do capillary zone electrophoresis. This should be an embedded movie, so this should work. That's where we go. We have our analytes. This is fluorescent, so it's negatively charged. going from the top to the bottom, change the polarity. I'll show it again. I'll show it 20 times. You'll get sick of it. But it's one of the things I can talk for half an hour. A movie does a lot better job. So we get the analyte going in the electric field, switch the voltages, and poof, it goes. So we don't need any pumps. We don't need any valves. We just need to have power supplies and play around with the polarities of the power supplies in order to get it to work. We've got another way of doing this. And you've heard me say it already when we were talking about lab on a sheet. This is called gated injection. And we still have a cross, but we use it slightly differently. We use it around the corner. Some people like to think out of the box. So we have, this one should have been here. So we've got our sample and our sample waste. And then our buffer and our buffer waste. Now our sample comes here from the left. So this should have been sample, sample waste, buffer, buffer waste. Because then we match the geometry there. I got the picture in a little bit later. So here we can see that we've got buffer coming from the right-hand side going down the separation channel. At the same time, we've got our analyte going from our sample channel towards the sample waste. Everybody's happy. We don't get any bleeding because we've got a little bit of buffer as well going here. So stationary system, we've got a channel with a potential difference only with background electrolytes. If we temporarily let our potential power supplies float, then all of a sudden there's no driving force for this one to go around the corner anymore, and it goes down a little, which then means that we've got a small sample zone up to the point where we restart this power supply, and we've got a small injection zone that we then have surrounded by background electrolyte, so we can do a capillary zone electrophoresis. Again, a movie where you can see the injection going. We've got a potential applied between sample and sample waste, buffer and buffer waste, and our electrophoresis takes place. If we temporarily hold this voltage, then all of a sudden there's a driving force for analyte to enter the cross section, enter the start of the separation channel. And if we only do that momentarily, we allow for a small amount of our analyte, of our sample plug, to enter up surrounded by background electrolyte in our electric field and do an electrophoretic separation. So you can see it just bleeds out, small enough to be less than 10% of the capillary volume, and it can be injected and separated by CE. This one is called the gated injection because you're temporarily open the gate to allow this plug to go in. We can also intentionally increase the injection volume doing this a little bit. So we've now been looking at something that's called the cross injection, using an injection cross. If we make the inlet and the outlet a little bit offset, then we call it a double T injector. Just terminology. If our sample channel is long enough, it doesn't matter what we do. But if, for example, we know that our analyte is present in very low concentration, and we still want to be able to detect it, we can detect 10 times, while we inject 10 times the volume, and therefore potentially we can detect 10 times as little if we don't have a lot of broadening going on. So double T injection, both pinched and gated injection apply as well. The difference between the cross injection and the double T injection is the sample volume that you inject. Most people will be using the cross, but it's a nice trick to have on your sleeve if your limit of detection is just a tiny bit too low for your sample amount. We've already seen this one. That's the nice advantage of both the gated and the pinched injection, is that you can also do it highly in parallel. It is just a matter of programming your power supplies, programming your potentials. You don't need pumps, you don't need valves, you don't need any other infrastructure. So the capillary array electrophoresis with the 96 and the 384 channels were both done using exactly the same system. We've also got some hybrids. And that is if we want to combine a system with some monitoring, similar to the hydrodynamic injection that I've just shown you. The Harrison group somewhere early 2000s had a very wide, low flow resistance channel to continuously pump sample through. Every now and then they would apply a potential difference to then do cross injection a little bit down the road. So here we've got the very wide channel. Here you can see this is technically a double T injector. They've only drawn the geometries a little bit crooked, but they could have sample going past the intersection towards sample waste and then doing the separation down that direction. So this is a double T injection geometry that has just been drawn very awkwardly. But if you kind of pull it apart, it's a similar thing. And here you can see the flow resistances where the large channel has got a very low flow resistance. So therefore, normally the sample is just flowing there and doesn't even notice the electrophoresis going on, up to the point this channel gets either is grounded or gets a potential to it. Then a little bit of sample is siphoned off across the intersection to the waste, which then sequentially can be separated by applying a potential difference between D and H. So that's the way that you can do a combination of hydrodynamic flow and electrokinetic injection. The field will win. There's a couple of great success stories that have used this, and Philip, we don't have him here, but our Mars analyzer is also based on our pinched injection. So we've had microfluidic systems certainly going to the moon. They're preparing for Mars to do some amino acid analysis work. Here we've got the capillary electrophoresis system. Here we've got the sample extraction system that both will be going, or should have gone up to interspace by now, because this is a couple of years old. This system in here, it's got high voltage electrodes in there and a fluorescence detection. It is does on-chip labeling, so amino acids are not fluorescent by themselves. So what the instrument does is that it adds a fluorophore to the sample that selectively labels amino acids. All the amino acids then have FITC, a fluorescent label attached to them. Then there is a capillary electrophoresis separation where the amino acids are using pinched injection loaded onto the injection cross and then separated electrophoretically and detected at the end by a light-induced fluorescence detector. Because the device has been used a lot of times over and over again, it is being cleaned with some sodium hydroxide to have the same starting conditions, and a glass device is being used in this instance to have that robustness to reinitiate the chemistry over and over again. So what we'll be talking about microfabrication next year or next week, but it is important to realize now that plastic devices are all most frequently done for single use. You can throw them out after you've done it. Glass devices, because they're such easy to clean and such well-known substrates, if we want to have a multi-use device, a lot of people will pick a glass as a microfabrication substrate. A little bit less glamorous one, called our lab on a sheep. I already referred to it. It's one of my favorites. I just like weird things. And we've seen it before. And if you remember what I was talking through, this one used gated injection. So very similar to the other paper with the hose. Normally the dialysate from the sheep was running here. But so this now becomes sample waste, buffer. Buffer waste kind of flipped to the other movie that I showed. But if we apply a potential difference, then our sample will move towards sample waste. And we'll have electromigration from buffer to buffer waste. We temporarily float the electrodes. So we'll have a little bit of sample coming down at this intersection. We then reactivate the electrodes. We get potential difference applied between buffer and buffer waste for our electrophoretic separation, followed by electrochemical detection, and you can do the rest. So a lot of these CE applications everywhere out in the fields are using this cross injection. The Agilent bioanalyzer. If any of you ever will end up working in a lab doing a lot of protein or DNA analysis, they sell the chips like this. They've got 12 reservoirs, can run 9 samples. I think, my next slide even is how. They sell a complete kit to do chip electrophoresis for the separations. It's based on the pinched injection. So the workflow is really, really easy. This is an instrument that you can buy off the shelf. You buy a whole range of different chips. It comes with a sample injection station. Sounds really advanced for those of you that have an engineering background. It is a block with a couple of little O-rings in there to get a leakage tight seal. And it's a syringe on a plunger that you can put down to put some hydrostatic pressure above the reservoirs. There's nothing really special about this chip loading station. It is a syringe that with a little clip so that the syringe barrel is being kept down. But Agilent sells it for a lot of money. This is then the capillary electrophoresis interface, where there's an array, all these 12 reservoirs that are in here, 16, there's 16. All the 16 reservoirs have corresponding platinum pins here that form the electrodes to do the electrophoresis. So you pipette all your reagents in, you apply your pressure to ensure your, in this case, you do gel electrophoresis, so it's a bit more viscous. Filling it by capillary action is a little bit harder. So you need that pressure to squeeze your background electrolytes into all your channels. And then here we can see it's our pinch injection, where a sample moves across the intersection towards sample waste. And then we apply our potential difference from our buffer to our buffer waste. When our analytes are surrounded by our electrolyte and exposed to an electric field, they separate into different zones. In the case of this Agilent bioanalyzer, these are either different lengths of DNA or different sized proteins. And the fast runners come past the detector first, the slow ones come later. You get detector signals, and that's the way that you can characterize your mixture, because you've got separated into its separate fractions. So our challenge now is to try to get you all to be able to draw the gate and the pinched injection for cations and anions. And I think I'll just first make sure that we've got these ones labeled the right way around, because otherwise everybody gets confused. So we've got, going from the top, so that's sample. That's buffer. That's better. So I'll show you the movie again. So we've got our sample coming down. So I'm going to draw on the board. You're going to tell me what the electrodes are. And we'll keep on doing this. Once we get it right as a group, you can go home. So we need to do this for the gated. Now for the gated injections and for the pinch. Once we can do this, I'm happy, and we've got an early afternoon. So we've got our chip, and can we put this one so that the people on Google can watch along? We move it around a bit so they can see the board. So I've now drawn the insides of a couple of microchannels. We're doing it, so we've got sample, buffer, sample waste, and buffer waste. I'm not sure yet how we're going to do the examination, but if there would be anything on the exam, this is already half your points. Label the reservoirs the right way. If we say that we've got our analyte that is an anion, it's negatively charged. What's the first thing that we want to do in the gated injection? Well, these are equilibrium state. Go slowly. Let's just copy the picture. So we want this one filled with sample and this filled with sample. I know I'm not an artist, but it's kind of similar to what's on the projected slide. If we've got a negatively charged analyte, what do we need to do? Is this one plus or minus? What do we do there? Here, pluses and minuses. That's the two options we have. Hands up. Who thinks we want to have plus here? Who thinks we need to have minus there?
Who thinks nothing? You'll think nothing. Okay, this is going to be a long afternoon. We'll be here till 5. Negative ion. Where does it move towards? Does negative ion move towards the positive electrons or towards the negative one?
Positive.
There we go. It wants to go here. Done. So we've got that one sorted. I don't like gambling, but if this is positive, this is never going to be positive. So that one will be negative. So the separation ones, it will be moving in the same direction, because this is where the good cheating starts. Because if we know that this one is positive and our analyte goes there, then for our separation, we want to have that positive here as well. We now only have one option left. That one's negative. Puzzle solved. So our potentials, if we talk about a negatively charged analyte, that's the way the potentials there have to look like. So we then want to move to the part where we fill the intersection here with our analyte. Of course, so just maybe let's. How did we do that in gated injection? Well done, great answer. We do nothing. We switched off all the power points. We just do nothing. Well done. We do nothing. We just let it flat for a little bit. Diffusion will do its job. And then we get back to what we did. So we said we've got our negatively charged analyte, so we want to chase it away from here. So we want a negative there, positive there, negative there, because we can still see it, positive there. That one back, but we now have our analyte sound sitting there in our electrolyte. But now. Excellent. I like the fact that you all knew that we were not doing anything. So we have our next scenario. Not the gated one. Let's look at the movie again. Movies are always good. So let's watch the movie and just be mesmerized and see what the power supplies are doing. So they're on, from positive to negative. We let them float for a little bit, allow the sample to leak out, and we switch on our power supply again. Very easy routine to be doing. Cheeky question before we go on to the next one. What would happen if our analyte would have been potassium? So it would have been a cation. Any idea what would happen with our polarities of our voltages that we apply for our electric freezers? They change around, they go to the opposite side as well. So if we understand what happens with the anions, it's exactly the opposite for the cations. So from then, the learning is not really hard. If we only understand it for one way, we can make it for the other way as well. Now the harder one. Because this was the easy one, because you have the answer right, because you do nothing in the middle. Just you've got your potentials right, you sit down and you relax, and then you do electric freezes. We don't want to do pinched injection. Let's keep our. So we're doing that orientation? Yeah, that's the easiest to not confuse you. So we've got sample, waste, buffer, and a long separation channel. Our detector. So that's the way that our electric freezers chip looks like. We kind of want to go to that picture again. So we've got sample all the way to the intersection. It's colored in. That's the way that we want the first instance our picture to be looking like. If again, because a lot of this work is done with fluorescing, which is negatively charged, we start off with fluorescing, which is an anion. What potential do we want to apply to our sample reservoir, positive or negative? Oh, we've got an early finish today. You're there. Negative. What do we then apply to sample waste? Done. How do we then realize the pinch? What do we do with buffer? Positive or negative?
Negative.
Good thinking. Buffer waste.
No negative.
Oh, we've got conversation.
Negative.
Let's hypothetically go for the scenario if this one would be positive. What would our analyte here do? I want to go there. And that's not what we want to do. Analytes are very simple creatures. So if you're thinking yourself through and you're thinking yourself stuck, just look at what would this analyte be thinking here. So we want to have this one negative, that one negative, positive, and we've got a beautiful reference. The only thing you need to think about now is that potentials are relative to one another. So if this one is at -2 and this one is at +2, our potential here, if they're equal length, is about 0. So we want to apply a potential that is slightly negative relative to the about 0 potential that we've got here. If we don't have a negative power supply, we may have this one at 0 and that one at +4 kilovolts. Still, our potential difference is exactly the same. But that means that this intersection is not at about 0 volts, but it is about 2 volts. Which now weirdly means that +1 volt is negative because it's smaller than plus. So if you're setting up a CE separation yourself, and you would find yourself in the situation where you work with a positive high voltage power supply and a ground, and you can't figure out why your analytes are going the wrong direction, calculate what your local potential is, because your analytes are pretty stupid. They don't see what the whole system is doing. They just know this is 2, and they're looking, what is smaller than 2? I'm going there. So this is, yeah, that's +4, now we want to have that one. It's 3. Oh, that's wrong direction. But that's just a side step.
Still in there.
Ah, there it is. So we've got our analyte that's sitting at our intersection, and we now want to do our separation. What do we do with the potentials? What potential becomes buffer? Negative analyte. We want to move there. Go to the separation device. Yeah. And then that one becomes positive. And then these ones we either have floating or we apply what we call a pullback voltage, which means that we want to have our analyte going negative analyte a little bit that way. So we want to have a very small positive here and a very small positive here. Because what then happens if we start with our separation going there with background electrolyte, it pushes this to the side a little bit as well. And we get a cleaner injection zone being injected. Because if we don't apply the little pullback voltages, then we get a little bit of drag of the analyte that's sitting here and there to come along. May make a difference of 1,000 plates or so in resolution. So most separation is not hugely important. If you're really trying to resolve 2 analytes that are migrating really closely to one another, this one may just make a difference to get baseline resolution and have a lot easier time quantifying. So, do you think you can write down pinched injection by yourself?
you just have a sheet of paper. And I'm not going to put anyone on the spot, but please get yourself a bit of paper and try to see if you can get the potentials right for a pinched injection of a cation. And I promise you that's the last thing to do today. You did great with the gated. We've done gated positive, negative. We've done gated of a pinched injection for an anion. If we do pinched injection for a cation. May even be charge is charge. It doesn't matter here if we've got 2 plus, 3 plus, 5 plus, plus is plus. See some satisfied faces. Let's go. So we've got the positively charged analytes.
Sample base is negative.
Sample please?
Sample base, positive sample.
Yep.
Sample base is negative. Buffer is positive. And buffer base is positive.
Well done. Just graduate. Separation.
Sample is positive. Buffer base is negative. Buffer is positive. Negative. Sample base is positive.
Positive relative to where? If we've got our, is it positive relative to that part or relative to the others? You are correct. You don't want this analyte to think this is negative, but then it wants to go there. So you want to have this one slightly positive relative to the intersection. So you've graduated 100% score. Are we having everybody along? Or do we have people that
Won't go through it another time. Happy to have you think tonight and do it again tomorrow morning. I'll show you the movie one more time. Think about the ions as if they're marbles on a marble track. They will only run where gravity goes. So they run down the hill. You change the orientation of the hill and they'll run down again. They run down, and off they go again. So that was it for me for today. It is not an easy concept, so draw a couple of crosses. Once you get your head around it, you're like, yeah, sure, that's the way it works. But it is a hard concept to get your head around because it's sometimes a bit scary to think potentials. It is hard to realize how voltages actually interact with an ion when you're doing electrophoresis. If you're struggling, I'm happy to go through it with you right now. Happy to show it again tomorrow. It is, once it's clicked, and it's clearly clicked there, it is obvious what's going on, but it is all the, 95% of the capillary electrophoresis devices use this for injection. So it's good to get your head around how the injection actually goes. And once you've got your head around this, it makes it actually easier to understand the normal electrophoresis that Professor Philip talked about this morning as well. Because it does make sense that ions are just stupid. They move around in an electric field unless they've got friends in the train pulling them down because you put any kind of other things that are interacting in your background electrolyte. Unlike chromatography, where there's a whole range of different stationary phases, electrophoresis is simple. Don't overthink it. So, thank you very much for coming. Rest on this, give it an hour, draw a couple of crosses, and trust me, every time I need to teach this again, and every time I haven't seen it for a while because I haven't done any CEs myself, I always, in my lab book, still draw the crosses, get the picture right, know what I'm going to do, and then I program the power supply. It is easy to draw out, it's very hard to put in your mind, and it's one of the things that you can't learn off a video. It is one of the things you just have to do the scribbles on your lab book or in your notes. And once you know the theory, it's always, you'll always find the answer. And if you've got the answer wrong, then you'll just see when you look under the microscope there, the analytes move the wrong direction. And then you'll just draw it out again. You're like, yeah, 2 is bigger than 3. Yeah, sometimes. So you'll get there. Good luck. Enjoy the afternoon in the sun.
So if you have any question, Varaji, the copy pencil with the before here. You will get to anything. You don't know where you will reach and at what time. Knowledge is super.
Yes.
So, thank you very much. And tomorrow we have another speaker and demonstration or if you can bring your laptop, you can enjoy more. And so you will get introduction to some softwares. You can download the software and do calculations also. It will be very nice. You can bring your phone. If you have laptop, you can or you can change it in the evening.
So he's developed a very nice package to simulate isopropylis. So to actually put in different items, look at their mobilities, create that window where you want to do the setting. Probably very nice timing that we've done this now where we know where the items are moving and we can simulate it and see where mobility plays a role. And one of the things that both Professor Philip and I haven't been able to touch on today is the importance on what components you select in the buffer. When do you pick a borate buffer? When do you pick a phosphate buffer? When do you pick frizz? When do you pick chest?
That is when you select which type, what pH, what
The nice thing about the simulations is that it makes life a lot easier because you can try 5 different buffers to get it right. And you don't spend a lot of time making up all those buffers and binding all your chemicals. So simulations are really useful in CE because there's, in a certain point, there's a whole range of different buffers you could